First talk of today is about data science. If you hear data science, you probably think big data, boring mathematics, statistics, some people playing around with Python and R on some stuff that has no impact on security whatsoever. To prove you wrong and to explain to you how data science can actually work together with IT security and stuff like that, we have on stage the wonderful Thordis with what has data science got to do with it. Please give a very warm welcome.
Thank you for the introduction, and thank you all for being here. I know it's very early in the morning, so sort of expecting a crowd of 5, so I'm very pleased to see that's not the case. What kind of sparked me to want to talk about this topic is that as a data scientist, one of the questions that I most commonly get is something along the lines of, when is the AI going to take over the world? And while I think it's fun to debate whether we're ever going to reach a state of developing something that actually has artificial consciousness, I think we are nowhere close to that point at the moment. We don't have, while data science is very powerful, we don't have any methods that are close to having that capability. So in this talk, I just want to shed a bit of light on what data science is, how it can be used in security, and give you some kind of tips to walk away with for how you can assess other people's data science solutions. So, and as this is an introductory session, I've purposefully left plenty of time at the end for questions. So I should have time to address any questions you have afterwards. The talk will be in 3 parts. So the first one is where I just explain what data science is. This is going to be a high-level coverage, so not diving very deeply into it, but just kind of giving you a bit of context so that we're all on the same page going forward. Second one is the biggest section, and this is where we look at a practical example of how we can use data science in security. And one of the key takeaways here will be that machine learning is not always the way to go, and I'll explain a bit further why that's the case, and when you can and when you can't use it later on. And lastly, we'll be looking at how you can assess other people's data science solutions. So starting with the first section, what is data science? I think a lot of both kind of marketing and media statements that go something along the lines of, the machine learning will take care of X, make it sound like data science is a bit of magic. But it most definitely is not. There's absolutely no magic involved at all. Instead, it's based on theories from fields that have been around for a very long time. So the core, as he touched on, is the maths and statistics. People kind of tend to find this the boring bit, but my background is math, so I actually find this super exciting. But this is where the theory comes from. This is what actually makes it possible, gives us the theory to optimize what we're doing, optimize the problem, and gives us a way to prove that what we're doing is going to work. Then, when these fields join forces with computer science, that's when the real magic happened, because that's when it actually became possible to implement this. So this is where we kind of get beyond what humans can do, because by applying the theory from maths and the power from computer science, we get theory that's possible to execute on a scale that no human ever could. And then lastly, what's sometimes overlooked is the domain-specific knowledge. And this is what actually makes it relevant. So this is where you get a human that's an expert in the field where the solution will be applied to come in. And first of all, just scope out the problem. Very clearly define what the research question is, and defines requirements for the solution. So these are things that the solution has to apply to, and is requirements that the solution, things the solution cannot do. And going back to the topic of the talk, what has data science got to do with it? By combining forces from these 3 fields, you get really powerful tools. And that's really what data science is. It's just a set of tools that can be applied in security as well as other fields. But by applying the domain-specific knowledge from security, that's where you get really powerful solutions that kind of get us further than we would without data science. And just for a bit of context to put things into perspective, because I know there's a bit of, there can be a lot of confusion about these terms and how they all fit together. This diagram is my opinion. It varies a little bit depending on who you ask, but it's something like this is what's generally agreed upon. So first of all, you have the data science. Data science is quite a wide field. It has a lot of methods and a lot of topics within it. Slightly narrower within that, you have advanced analytics, and then lastly, you have machine learning. So you'll often hear data science and machine learning referred to almost interchangeably, but they most certainly are not. Machine learning is a core part of data science, but it's only a subset. It's not the whole field. Because data science is a field that's grown very quickly, technical literacy hasn't quite caught up yet. And this has meant that a lot of parties, either purposefully or unpurposefully, not judging here, but they have kind of taken advantage of this. And you hear a lot of statements using jargon that, you know, it's usually terms that actually mean something, but the way they're phrased in the sentence doesn't actually end up meaning much at all. It's made to sound impressive, oftentimes complex, and it's they're kind of made to make you just go, okay, they sound very intelligent, they must know what they're doing. But one of the points that you should definitely take away from this talk is don't trust those people. I mean, they may be very intelligent and they may be doing something really clever, but don't just take it as truth unquestioningly. You have to actually dive deeper, and you need to ask them about what's going on. Because if someone can't explain what they're doing beyond, I'm using deep neural networks, that is not a solution that you want to use at all, as a big warning sign. So to wrap up this section about what data science is, I'm just going to end with this quote from Garry Kasparov, which I think is quite good. So he quite famously was one of the first chess grandmasters that was beaten by a machine learning algorithm that was trained to play chess. And this is a quote that he gave in an interview where he was talking about machine learning. And he said, people think we are Windows 10 era, while we're still at MS-DOS. Oh, sorry. Let me put this down. Oh, what's going on? Okay. But anyway, I think this summarizes it quite well, because while data science, you know, obviously I'm a bit biased, but I think it's amazing. It's got so many powerful tools, and it got so much potential. And we are always getting further and further as well. So it is definitely a field that has a lot of potential, and I think it's just going to become more and more relevant. But we do still need to put things into context and remember that it's not like you can just apply the data science and get the solution. There are a lot of requirements that need to be met, and there is a long way to go still. So on to the second section, where we're going to be using data science to tackle security problem. So to make this relevant, because the first section was obviously a little bit theoretical, now we're going to apply it in reality. And we're going to assume that we're working at an organization that wants to reduce the number of devices that get infected with malware. And we're going to go, because there's a lot of ways that you could solve this within data science. God, I'm mixing it up now. But the first that I'm going to talk about is a field that I think often doesn't get enough credit, and I like to call that not machine learning. The second area that I'm going to focus on is machine learning. So these two ways are going to give us slightly complementary views of the problem. So the not machine learning, there's a lot of things that fall into that. You have a little bit of data engineering, and you had a lot of kind of data analysis and statistics. So by applying statistical methods, we're going to get a view of what the current problem is. So we're going to take the problem as it is and break it down into something that's less complex and more easy to deal with. And that's going to give us an answer or give us an insight into what the current solution is, and from that we can kind of decide what actions to take. With the machine learning, that's a slightly different different view that we're getting, because there we're assessing something that we haven't seen before. So we will use the data to train a model and get a prediction about what might happen in the future. So this is more about how can we future-proof ourselves. In this case, we're very lucky because we have a data set available, which oftentimes in data science is a big pain point, because you need to have an extensive and you need to have a good quality data set. And while there's a lot of questions that would be interesting to look into, a lot of times it can just be very difficult to find the data to actually solve it. But in this case, I'm going to be relying on a publicly available data set that was published by Kaggle. And so this is a data set about malware predictions from Microsoft. So just to get a sense of what the data set looks like, it's actually huge, so I'm definitely not going to be using the whole data set because we'd be here forever otherwise. But I've kind of pulled out the key things. So first of all, we have device information. So as I said, there's a record per device. So we have an ID, we have some information about the type of device, about whether it has a firewall installed, and the platform. Secondly, we have some information about the AV. So we have the number of AV products installed, number of AV products enabled, and the name of the product. Then we have some business information that helps us break it down in terms of our organization. And lastly, we have a label for whether this device had a detection or not. So starting with approach number 1, the not machine learning one. I'm just going to look at some very basic statistical methods here, but just to give you an insight of how a data scientist would go about starting to solve this problem. And actually, to be fair, I, as a data scientist, spent the majority of my time working in this area, because even if you are planning to apply machine learning, you almost always need to start by applying statistics to actually understand the data. So what I've started doing here, and what I think is usually the best way to start, is focusing in on some dimensions that you think matter to your problem. So in this case, I've chosen the number of AV products enabled. I've grouped the numbers into has detection versus does not have detection, and counted the number of records in each category. So now we already have some insight, but I, for one, would definitely find it a little bit tricky to take any action of this, because the numbers are very different quantities, there's a lot going on, it's quite difficult to interpret. So the next thing we could do is going from counting to calculating the percentage. So this is the percentage that has detection or doesn't have detection per number of AV products enabled. So now at least we've normalized the data, so we can start to compare the devices that have, for example, no AV products enabled versus the ones that have one AV product enabled. But again, there's quite a lot of numbers, so something that I think would be quite useful here would be to visualize the data. So here I've just plotted up the percentage of devices with detection per number of AV products enabled. So already it's become so much easier for us as humans to interpret the data, because we can look at this and already draw out some patterns. So for one, we actually see that the most prevalent class of devices to get detections is devices that have one AV product enabled. Now, I definitely would have thought that if the AV products were correctly installed, enabled, and configured, that should decrease your chances of getting detection. But however, we see that that doesn't seem to be the case. And in fact, it seems like having no AV products enabled is actually the best thing to do here, because all the other classes have a higher percentage of detections. So these were the statistics that would take you around 2 minutes to do, but you could already draw some conclusions, because we can see here that there must be some problem with the AV, so we can ask ourselves questions like, are the AV products correctly configured? And we can start to take actions and dive deeper into the problem from there. In reality, not all devices or you don't care about all devices the same amount. As an example, if you have a device that's decommissioned, not connected to the internet, you probably don't care as much about that one as another one that's running a critical business application. So in reality, what you'd always want to do is to focus on what matters most to you, because you want to see which part of your set would be the worst if it was damaged. What would cause you the biggest harm? So in this example, I've assumed that we have a list of the 20 most important devices in our organization. Because if we are tackling this problem logically, we'd probably want to start there and then work our way from there. So now I've just filtered the data to only look at these 20 devices. And now we actually see that out of all of them, 3 of them have a detection, and actually all of them belong to the same organizational unit. So now we can start to ask ourselves, what's going on in this unit? And something that would make sense to do next is to go and actually look at how the AV products are configured in this organizational unit. Sorry. Okay, key takeaways from the non-machine learning section. So this is something, if you were to apply what we've gone through here on another problem, the first thing I'd always say makes sense to look at is look at how key characteristics affect outcome. So in our case, we saw that the number of AV products enabled didn't affect the chances of having a detection at all. Secondly, focus on the part of the problem that you care most about. And this is because we're working in real life, and while in theory you definitely want to solve everything, in reality you have to start somewhere and then work from there. On to the second approach, machine learning. So the goal here would be to predict whether a device is going to have malware detections or not. So as we said before, this is a slightly different view. Now we're gonna assume that we know what the current status is, and assume that the current status is representative of the future, and that we can make some predictions based on this. So in machine learning terms, we're gonna train a model to give us a true or false outcome. So this is a binary classification problem. There's a lot of different ways that we could go about solving this. Even after we've decided to solve it using ML, there's a whole host of classes of algorithms that we could choose to use. We're definitely going to be focusing on the binary classifications here. And what we're going to be doing is, as I said, we're going to be taking the input data. We're going to, after we train the model, we're going to have some data that we want to apply it on. So this is the same data as before, but now we don't have any information about whether there is a detection or not. We're going to plug this into our model, and we're going to get a prediction for whether this device has a detection or not using the model that we trained. So focusing on the different sort of algorithms that we could choose to handle this problem, as I said, there's a whole host of them. And I've sort of chosen to focus on 2 that are in some sense on the opposite sides of the spectrum out of binary classification models. So firstly, logistic regression, and secondly, binary neural networks. And I'm just going to go through some of the pros and cons to kind of highlight to you how different they are. So first, if we look at transparency, logistic regression is very transparent. The output is just a formula that you can calculate yourself. So if you want to understand why an outcome is reached, you can just look at the formula, and it's very clear. With neural networks, that's not the case at all. It's a complete black box, so once you get an outcome, there's no way of telling where that outcome came from. And there have been a lot of interesting cases that have come up around this. For example, in healthcare, there are examples where machine learning algorithms are making way better predictions than humans are, and the doctors have no way of knowing where the prediction came from. And then you reach this interesting dilemma of, do we actually apply it or not? Because you don't know how it's being made. Is it being made on something sensible, or something that's maybe just correlated but not an explanatory variable? So there are reasons, or there are cases when the fact whether the algorithm is transparent or not is going to make a lot of difference. Secondly, logistic regression is really simple, and neural networks are not. And in general, I think when you have 2 algorithms that perform similarly well, I personally would always go for the simple choice, just because when you go for a simple option, you reduce the chances of you overlooking something, because when you don't understand completely what's going on, there's a lot that can go wrong. So this is definitely one of the kind of key benefits of logistic regression. Efficiency to train. Logistic regression is very quick. Neural networks, not so much. Works without much data pre-processing. So logistic regression, because it's very simple, it requires the person using it to have done a lot of manipulation on the data before you actually train the model. For example, it doesn't handle correlated variables very well, Whereas the neural networks, they're a bit more clever and they can see past things like this. So the prep necessary for logistic regression is significantly more than neural networks. Neural networks are also a lot more flexible. Because the output of the logistic regression is essentially a linear formula that's then plugged into another transformation, you have a requirement on how the two classes are separated. So as I said, they need to be easily separated. So that means if there's a lot of overlap between the true and the false, so in our case, has detection versus does not have detection, the logistic regression is not going to handle that well at all, because they're going to try to, or that algorithm is going to try to create a linear separation between them, whereas the neural network doesn't make any such assumptions and can work in a way more flexible case. This is one that has made neural networks stand out quite a lot in recent years. So whereas a lot of the kind of older, neural networks are old as well, but the algorithms that have been famous and commonly used for a long time, they improve up to a certain point, but after that, it doesn't matter how much more data you get, they're generally not going to get much better. Whereas neural networks almost just improve linearly as you add more data. So now that we have more processing power, more data available, this has really made neural networks stand out. And then lastly, a bit of a con they both have in common, they're prone to overfit the training data. So this is something you've got to be really careful of, because it can be easy to look at your training data and say, oh yeah, my model performs super well, but if the training data is not representative of the testing data, it's not going to handle that very well. So as you can see, these two classes of algorithms are somewhat on different sides of the spectrum. I'd say generally people kind of tend to look at neural networks and think they're really cool and think therefore they're better, whereas they're both just suited to completely different cases. And I actually think the logistic regression doesn't get enough credit at all, because it is simple, so people kind of think, oh, it's not exciting enough, you're not going to achieve good enough results. But that's not really the case at all, and there's actually a lot of cases when logistic regression has been deployed very successfully in the real world. And in general, because it's so simple, it actually a lot of times makes sense to start with that as a baseline anyway, and then kind of work from there if you want to improve. So now that we've had a bit of a long discussion there about pros and cons, I was just going to do a bit of a demo of how this works. And I want to get a show of hands. Who wants to do logistic regression and who wants to see neural networks implemented? And again, this is to handle the problem we discussed before. We're going to make a prediction about which devices are going to, or we're going to create a model that's going to make predictions about which devices are going to get malware detections and which ones aren't. So could I just get a show of hands? Who wants to see logistic regression? Okay. And what about neural networks? Oh, it's about even. Okay. Okay, I'm going to go for neural networks then, because I was kind of sure that people would choose that, so that was the one I prepared for more anyway. Oh, where's my mouse gone? Okay, so what we've got here is just a notebook. And to save ourselves some time, I've already preloaded the data. So the first step, actually, can you see this properly, or can I? Actually, let's do like this. So first step, this may come as a surprise or may not come as a surprise, but when you apply machine learning, you actually don't do a lot of implementation of code in general. So the actual machine learning algorithms have already been implemented by someone else and are available open source. So what you always end up starting by doing is just importing a lot of stuff that other people have created. So that's what we've done here in the first row. Then we just read in the data, and to make this a bit more performant, I've reduced the number of rows to the first 100. Obviously, you wouldn't do this in reality, but for demonstration purposes, I think that's a lot better. Don't really need to worry too much about this, but this is just where I'm cleaning the data, because when I read it in from a CSV, the computer doesn't know what type of data all the fields are, so I just need to kind of convert them to the expected format. And then I separate the data out to features and labels. So features are all the variables that are not the has detection, doesn't have detection. So these are the device categories, the organizational units, the business context, and the AV information. And this is where the magic happens. This is where we create our model. So again, this is all just based on code that someone else has implemented, so what we need to do is super simple. First of all, we just use this library to create the model. In this case, we add one layer, because I'm keeping it simple. So we have one layer with one neuron, and we have an activation function that, again, someone else has implemented, but I can just refer to. And then we just compile the model. And all we're doing here is we're telling the model how to assess whether it's doing well or not, how to kind of minimize the loss. So here we go. Now we've created our model. And then we fit the model on the data. So as I said, the features are all the information that's not the label, whether it has detection or not. Labels is what to fit those features to. And then this is just, these are just some parameters for running the model. So here we go. And we've done it. We've created a neural network to solve this problem with 99% accuracy on the training data. So can I get another show of hands? Who would feel comfortable deploying this model on their estate? Okay, that's good. That's definitely the correct answer. Because as you can see, we didn't do anything clever. We just created a model with one neuron. We haven't taken much consideration in what our data looks like. We haven't validated whether neural network is even the correct choice of model. So I'm very glad to hear that all of you agree that you wouldn't deploy this. And in reality, when developing a machine learning algorithm, there's a list of requirements that need to be met for it even to make sense to design a machine learning algorithm. First of all, you need to have a clearly formed research question. And I mean, this may seem like common sense, but this is actually usually one of the toughest parts of solving the problem. Because it can be really tempting to, let's say we're developing a self-driving car, just to say, I need to get from A to B. But the machine learning algorithm is always going to take the most efficient way of getting there. So what they wouldn't know is that they're supposed to drive on the road, it's supposed to stop on red lights, not hit pedestrians. So you need to be super careful about how you phrase your research question. So for our case, a bad example would be, what can I do to improve my AV program? Because there's no way that a computer can interpret this to make any conclusion. It doesn't know what improving an AV program means. So a bad choice would be something along the lines of, does having an AV product enabled decrease the chances of having a malware detection? Secondly, you need to have good quality data. And this is quite a large topic, and it's really, I mean, this could be a whole other talk about what it means to have good quality data. But there's a few things that few requirements the data needs to meet. It needs to be accurate, it needs to be complete, it can't be biased, and the list goes on and on. So a bad example here would be, for example, to only use data from the UK, but expect the solution to also work in the US. And this is actually quite a common problem. It's to train the model on a subpopulation and then deploy it on a bigger population and assume that the same works there, but that's just not always the case at all. And this happens quite commonly in real life when, for example, a solution is trained on data that only refers to adults, but then you try to apply it on children. And children just don't work exactly the same way as adults do, so you do need to make sure that you include representative data. So so the good version here would be to make sure that the training data is representative of where you want to deploy the solution. Lastly, you need to understand the overall potential to cause harm. And there's a lot of ways in which you can tune your model, and you do have some power to decide how happy you are with, or whether you care more about falsely predicting a true or a false, for example. And an example here would be, for example, if you're developing an algorithm that predicts whether someone has a disease or not, wrongly saying that they have the disease is a lot less harmful than wrongly saying that they don't have the disease. Because if you say that they have the disease, at least you can do a second check and realize, oh, actually, that was a false positive. Whereas if you wrongly say they don't, there's less chance they'd follow up on it, and that could have really bad consequences. So this is something you need to take into consideration. It depends on the problem, how much it matters, but it's definitely something you do need to think about. So a bad example here would be just overwhelming the security analyst with alerts. So you do need to make sure that the solution is actually useful. A better alternative would be to consider the impact of false positives and false negatives. So in this example, do we care more about overestimating the number of detections or possibly missing a critical detection? So just to give you some examples from the real life, because these requirements may seem simple, but a lot of times they aren't met, and because there's a lot of things that need to be thought about here. So first of all, I've blurred out the names of the companies, because the purpose is not to shame anyone, it's just to show you that these things do go wrong, and it's not just kind of theoretical worrying. So a face ID algorithm that was defeated by a 3D mask. Now, obviously, it's very difficult to foresee everything that the users could do, but it's also very naive to assume that the users will just use the solution as intended. So you do need to think about, when you're forming your research question, what are the possible things that could go wrong, and how can I decrease the chances of that happening? This is one that went viral, I think it was either this year or last year, and was quite a big one. So this is one of the big companies that had developed an AI algorithm to help them with recruiting, and it favored men for technical roles. And this one was actually something, so what they'd done is they just trained on historic data, and it didn't seem like they were doing anything wrong, but what they'd completely overlooked is that they hadn't hired a lot of women historically. It was only recently that the number was growing. So while the reasons for that were probably completely unrelated to their technical capabilities, the algorithm didn't know that, and the algorithm just saw, okay, we don't want to hire women, therefore let's continue to hire men. And lastly, so this is an algorithm that had to be cancelled after unsafe treatment recommendations. So this is again kind of going into looking at whether you care more about false positives or false negatives. So the key takeaways from this machine learning section: not all machine learning algorithms are created equal. So as we looked at with the example of logistic regression versus neural networks, we saw that the pros and cons are very, very different. So you do need to make sure that the pros and cons match for your solution, because it's not like one is objectively better than the other, but one can definitely be objectively better for your specific case. Secondly, machine learning can only be applied when a list of requirements is met. And I think if you take anything away from this presentation, this might be the most important point. So I might just reiterate, machine learning can only be applied when a list of requirements is met. And just to go back over these are clearly formed research, have a clearly formed research question, have good quality data, and understand the overall potential to cause harm. So now going back to the real world, because in reality, I mean, while I hope I made data science sound a little bit more interesting than just boring maths methods, I assume most of you are going to continue working as security professionals. So now stepping back and assuming you're on the other side, so you have, someone is presenting to you a data science solution they developed, and as we saw, for it to be a good solution, there's a list of requirements that need to be met, but how can you actually validate whether it's a good solution or not? So here's a quote: "Our solution provides unlimited information and insights driven by leading artificial intelligence." Now, this is a quote that I got off a website from a company. I've altered it a little bit because I took out 2 or 3 words, but it's pretty much the same. It's the same essence. And if you really think about it, we could apply this to the machine learning algorithm that we developed. If we were to sell our solution, we could definitely say this. I mean, there's some subjective things in there. I mean, you could argue that what we developed was probably not a leading solution, but it's not clearly incorrect. So So if we now imagine we're on the other side and someone says this to us, how do we know that what they did was better than what we did in that demo there? So I've just created a bit of a cheat sheet here for you for questions that you can ask to get beyond the buzzwords, get beyond the kind of simple marketing of a solution. So first of all, just what do you mean? Because if they just give you a statement like the one we saw before, it doesn't actually tell you anything about what the solution does, or whether it's a good one or not. So definitely ask further about what they mean and why it's a good solution. How specifically did you use, in our case, neural networks or artificial intelligence? And this is going to matter a lot, because imagine that the solution is being used to make critical decisions. Then you're going to care a lot about the accuracy and the false positives and false negatives, whereas it could also just be used to optimize the whole process. So it's important to understand how it was used and why it was used. So yeah, why did you choose to use this? Going back to my point before, I personally prefer, if you have two solutions, to go for the simpler one. So I don't think it makes sense to, use neural networks just to use neural networks. It makes sense to use neural networks if they make the solution better, but you shouldn't use them, you shouldn't add unnecessary complexity unless there's a reason to do so. How was the model trained? So I'm not sure how much they'd give away on this one, but it's definitely worth asking them to get a bit of an insight into, could they possibly have data of sufficient quality to create a model of sufficient quality? Can I validate the decisions being made? So this is mostly when the decision is being used for something critical. How do you minimize false positives or false negatives? Obviously this is going to matter more in some cases than others, but it's important to ask them to see whether they've even thought about it. And lastly, just don't worry about asking naive questions, because I know a lot of these statements are made to intimidate, but it's important to remember that complex does not mean that a solution is better. And so really just ask about anything and don't let them get away with some fancy sounding statements that don't mean anything. And if anyone's interested, I was thinking of sharing a more detailed version of this cheat sheet on Twitter, probably next week. But just so I'm planning to elaborate a little bit more so that you can actually use this, because it may seem a bit abstract with just the questions. So, going back to what was this talk all about? If you weren't listening at all to the rest of the talk, just remember these 2 points. So firstly, that data science provides a lot of powerful tools that you can use in security. Sometimes stats are the way to go, other times machine learning is the way to go. But machine learning only makes sense in certain cases when the requirements are met and when the pros and cons of the algorithm align with your requirements. And you should ask about anything that's unclear. Don't just take any statements like holy truth. Do ask further questions. And remember that some of the marketing statements are completely meaningless, and you can always use the cheat sheet to actually assess how good the solution is. That is the end of the talk. Does anyone have any questions?
Thank you very much for the wonderful talk.
Thank you.
With impeccable timing, we have 10 minutes for question and answers. So if you have questions, please raise your hand and wait for me to get the mic to you. And coming from the cheat sheet, there are no stupid or otherwise unimportant questions.
No, exactly.
I first of all thank for your talk. Coming back to the cheat sheet, you said, can I validate the decisions made? Isn't this one of the main problems for any machine learning, artificial intelligence solution, that you can't validate how the decision is made?
Yeah, so a lot of times you can't actually, in most cases you won't get access to the algorithm itself. So it's not like you're going to be able to see, this is the formula, let me plug in and see what happens. However, in some cases you will see the output. The output will be in a format so that you can see, for this thing, this recommendation was met. For this thing, this other recommendation was met. So in these cases, you can look at that and see how you agree with it and compare with what you would think was expected. In other cases, it would be used to take some other decisions, so the actual output is kind of hidden, but it's definitely worth asking whether you do have any access to the outcomes, even though you don't have access to the formulas themselves.
Well, basically, yes, with the increased complexity of more or less nodes, for example, what you were mentioning, in my opinion, I'm not a data scientist, but in my opinion, that with the increased complexity, you will have real problems in more or less having, the proof that based on this input, this is the prediction, and which will then be used as an input for more or less a chain.
Yeah, exactly. So so neural networks, for example, they are always going to be a black box. Even the person who developed it is not going to know how the decision was made. So there are cases in which you won't be able to tell at all. But it's just important to if you can know how it was made, to get that information. If you can't, then so be it. But in general, specifically in security, if you're using these solutions to make important security decisions, I think it's quite bad if you can't tell how the decision was made at all. So that might be a reason why you might want to avoid that particular solution. So it's just all about kind of weighing up the information you have versus what you need.
Further questions? Yes.
I have always heard this idea floating around that you could simply learn what is normal, for example, in a network, and then let an artificial intelligence flag everything that is not normal. Is that a valid research question, or is this just stupid?
No. So what you're talking about is kind of what's called like outliers. You're finding outliers in essence, and I mean that is a very that's a solution that's often applied. And I mean, it is valid to look at what's normal, but you do need to think whether what's normal now is also going to be normal in a month and 2 months, and is what you're considering normal, is that normal for all use cases? So there's a lot of cases where you can actually validate that your normal is representative enough of the normal in the future where the solution is going to be applied for that to make sense. So that's a completely valid research question, given that you've looked at the requirements and made sure that it's going to hold true where you're using it.
As Douglas Adams said, we will reinstate normality as soon as we know what normality is.
Yes, exactly.
Any further questions? We have a wonderful data scientist on stage. Now is your chance. No further questions? Okay, you will probably be around today, right?
Yeah, I'll be around.
So
you can
just
come
chat
up to
her
me and
up.
ask questions if you want. I'm
Otherwise,
always happy.
thank you very much, Thordis.
Thank you.